been a hell of a lot of innovation in trackbed investigation and design, remedial measures, that sort of thing in the past. Well, since I sort of joined the railway 38 years ago, and particularly since privatisation. I'm not going to go through all of them, but I'm going to talk about recent developments in investigation in a brief way. We've also got different trackbed treatments which have sort of reduced the amount of work required to actually renew the track and solve some formation problems. The problem that Steve Featherson alluded to was sort of ballast, dirty ballast. In my experience, some ballast seems to last forever, and other ballasts seem to be completely shot within 10 years. So I'm going to say a few words about that. Another big problem is all this investigation generates tons and tons of data, and we've tried in the past to have a database to store reports, to store the logs in Excel format so we can sort of retrieve those. But it's very difficult to actually get the analytical sort of features so you can actually use that information and sort of draw on it. And there are systems available now. Network Rail have their LADS program. We have our own system. So I'll just talk a bit about sort of how these are being developed now. And also how we're using track geometry car data to try and diagnose failure modes. And then I'll hand over to Peter, and he's going to talk about some of the sort of quite substantial innovative treatments they've developed for trackbed. Some developments in trackbed investigation. From a safety aspect, we've been doing ABS now for 15 years, but it involved beefy chaps sort of lifting about 30 kilograms and sort of pressing a hammer and sort of shaking themselves to bits. So we've put that on a little trolley, mainly at Network Rail's insistence that it was sort of strictly speaking against health and safety rules. So we now don't have to sort of lift heavy weights and things like that. Only wants to kind of put it all together. So that's the mast operated ABS. We've developed GPR now from the old days. We used to have to sort of hold it, a man walking along the track, putting it on every crib, but it's now vehicle mounted. Network Rail sort of have it train mounted, and they measure their tracks sort of main lines once every year or once every 2 years. So, and there's a lot of improvements in data processing, which Peter will sort of go into. Another big development is this machine here, the rail track form stiffness tester. That actually tests the stiffness of the track formation and makes direct measurement. Until recently, it's only really been used where we suspect you've got very soft or poor subgrade, but there's now sort of increasing concern that the track can be too stiff. And for example, one of the treatments that's now being recommended is they have undersleeper pads. But undersleeper pads only work best if you've got a very stiff formation, and they're actually quite expensive. I think they're about £100,000 per mile to, in addition to these renewal costs. But it's hoped that if you use more of them, they're going to come down to about half that price. But the rail track form stiffness tester would actually say whether you actually need them. So at AECOM, I'm not supposed to sort of push on my own company or anything like that, but the process of actually organising the investigations and getting the results in, it's become a lot more efficient. We've developed sort of systems to actually make that quite a smooth running process. Just going to say a brief word about anti-pumping geocomposites. When I joined the railway, you put something like a 300mm layer of sand if you had a formation problem. It was called a sand blanket, and that would require vast amounts of excavation. You couldn't do much work, that sort of thing, but in recent years, two companies have now sort of started producing these anti-pumping geocomposites. So you can have a microporous filter, which actually is like the same porosity of sand. It'll let water be squeezed upwards, but in effect it's impermeable. It sheds water that falls on the track. So they're expensive, but can save time, excavation, and you reduce the need for new materials, which sort of reduces the need for sort of ballast trains and things. Okay. And you can use these in connection with geogrids if you've got subgrade erosion problems and you've got a soft subgrade, you can put a geogrid in on top of that. Ballast. I say some ballast seem to last forever, some ballast break down incredibly quickly. That's a SPRINGBOX. We tested 4 different types of ballast in the SPRINGBOX. And SPRINGBOX consists, as the name suggests, as a box, and 2 sides of the box are supported by springs. And if you put stiff springs in, it represents a nice stiff formation, good confining pressure. If you put soft springs in, it represents quite a soft subgrade. So the foundation flexes and you get more strain. So that's kind of simulated by the sort of soft springs. So what we found, if you look at the yellow ones, that's the stiff springs. Some ballast, and I can't remember what the geology of the ballast was, but some produce virtually no fines at all, but some produce, well here it's kind of 0.3. The test is basically you put 1 million load cycles onto the ballast, and then after the test you wash it and you sort of weigh all the fines, and what we're showing here is a percentage of fines produced passing the 16 millimetres after 1 million cycles. So that's 0.3. That's the maximum with the stiff string. So 0.3% of fines may not seem a lot, but typically you get 20 million cycles a year. So in 10 years you get sort of 200 million cycles. So you can soon see that those fines build up. So just with the sort of different types of ballast, you get a factor of 5 difference in the rates of fines produced. But if you look at the tests with soft springs, i.e. allowing more strain in the ballast, then that doubles the production of fines. So there's a factor of 10 just in this simple test. There's a factor of 10 in the rate of fines production. Okay, so the conclusions we draw are that perhaps the tests that Network Rail or railways throughout the world currently use, Micro, Duval and Los Angeles, aren't the right tests to do, because they don't actually test the ballast in the same way as it's actually sort of loaded in the track. I mean, basically both of the tests, you kind of just put the ballast in a big machine and sort of churn it round, and basically you're sort of exposing the ballast to sort of new particle contacts all the time. So bits of ballast chip off from everywhere, whereas in the track the particle contacts kind of stay in the same position. So the mechanism's completely different. Okay, and the other thing is that ballast actually lasts longer on a stiff formation. So we should be stiffening the track wherever possible to actually reduce ballast life. Vast amounts of data generated, so I'm just going to show the system that we've developed for actually managing the data. It's all stored in a vast database. Don't know how it works, I haven't developed it. And it does various things, presents all the data in a linear form, and you can drill down into the data, and you can sort of have a look at sort of what sort of material you have at a particular depth, look at all the test results, etc. So that's quite a powerful facility. But one of the things we're trying to develop at the moment is to actually improve the analysis of track geometry data, and try and work out from the sort of way in which the track geometry deteriorates with time, what sort of failures you get. And the first stage was actually to align the data. So this shows some Network Rail data. I think we've got about 40 odd traces there. And rather than just look on an 1/8 mile basis, we've got a rolling standard deviation, which allows you to sort of pinpoint problems more accurately. So that sort of shows on the bottom. You can see what happens if you have an 1/8 mile approach. That's okay for monitoring track quality and seeing where your problems are. If you want to actually solve the problems, you need to sort of hone in a bit more on where the real problems occur. So the middle graph, what that shows is the blue line is the rate of deterioration on this rolling SD. The red line shows the improvement in track quality for every sort of location along there due to maintenance. And from the data, we can actually determine how often that every bit of track's been maintained. What we found is you can't actually go or take track maintenance records too seriously, because I shan't go into that. But we think we can actually find we can identify where the track's actually been maintained from the data, but it has to be properly aligned. And you can see when it's aligned, you can see where all the problems are. And I assume they are weld positions or probably jointed track, because you can see where all the problems actually occur. One of the things I think we can tell from the data is earthwork problems and sort of where earthwork problems might be developing. So I'll just quickly sort of describe what happens when you have an earthwork problem. Just look on the left there at the top, the vertical alignment. If you have a sort of a shoulder earthwork failure and the bottom of the or the end of the sleeper drops, then the SD of the left rail deteriorates at a faster rate than the SD of the right rail, and that's accompanied, if you look at the bottom there, by sort of an increase in curvature or increase in SD. We did go into other things like crossfall and things like that, but couldn't get anything from crossfall. So we just looked at the sort of raw data, and what we've plotted there is the sort of the rolling SD at a particular point. We plotted the lateral alignment, the SD of the right top, and the difference between the SD of the right top and the SD of the left top. So the middle one, you can see that the right top's hardly deteriorating at all with time. That's that sort of 4 years records. But the lateral alignment, you can see that that's deteriorating all the time. You can see where it's maintained in 2011, deteriorates again, and then it's maintained at the end of 2012. So, and you can see that deterioration rate gradually increasing with time. The reason why we're looking at this is this is actually a site where you actually had a failure. Okay, and if you look at the difference in top SDs, that also follows the same sort of pattern. You can see the deterioration increasing incredibly at the end. We found that by just looking at the sort of the rolling SDs on a sequential basis, that shows the sort of behaviour over a period of time. You can quite clearly see where these earthwork problems are occurring. So there, we've got the same sort of 3 plots. We've got the right top here, so you can see the right top's hardly deteriorating at all, but you can see the lateral alignment is sort of going off, and you can see the peaks where it's maintained. That's matched almost exactly by the differential top. Okay, so that's earthwork problems. We also use the database to try and sort of predict how the track's going to respond to sort of changes in maintenance regime, increase in traffic, that sort of thing. And we've kind of put all our knowledge and understanding of the way in which ballast deteriorates, the way in which ballast behaves under soft and stiff formation, built all that in and come up with this system of trying to predict how the track's going to behave under different sort of regimes. So what you see there is the purple is the rate of deterioration, the blue is the mean quality, and the green is the sorts of interventions. Okay, so what the program first does, you have to preset trigger levels above which you maintain or above which you renew, and it automatically sort of shows what the maintenance regime has to be. But then you can sort of preset things like there, it's preset formation treatment, and in a moment it'll sort of, we've done that bit. That's sort of programming a ballast cleaning, see what that does, and it'll predict what happens there. And then you can also see what happens if you increase the level of traffic with time. So it's increasing at kind of 50 million tonnes a year. This is Australian track, So that's what happens if you increase it to 200 tonnes and you're sort of maintaining several times a year then. You can also see what happens if you say, well, I'm going to relax my maintenance standards or maintenance trigger levels, see how often you have to maintain them. So yeah, that's kind of being developed at the moment. So okay, so at that point I'm going to hand over to Peter, because